for turning up. We have David MacIver, who will be doing something which I know is very, very important to me, and I always get lost a lot. So he's going to discuss algorithms for solving mazes. Take it away, David. So please, big round of applause.
Thank you very much, John. So yeah, I'm here to tell you today about one of my favorite algorithms, which is a thing called L-star, which was invented back in the 80s by a researcher named Anna Englund. And unless you're John, you're probably not going to ever need this algorithm, because it's something I'm telling you about because it's theoretically neat, and I think it's a lot of fun. And I found that trying to understand it and understand it better has taught me an awful lot about how to reason about formal languages and a bunch of things. But like, this is a talk about its algorithmic appeal. Whenever I've tried to use it in practice, almost inevitably what's happened is I've come up with a much simpler and faster solution than actually using this algorithm. But on the other hand, like, it has often guided me to that solution, so that's useful in its own right, even if I've never run it in production and probably never will. So for the purpose of this talk, we are all robots. We are a little robot that is lost in a maze and has been tasked with the job of mapping it out. The mazes will be mapping, and the maps we'll be drawing look like this. If I occasionally look surprised, by the way, it's because I had to reformat all of my slides 10 minutes ago, so not all of these look quite like I expect. And yeah, so here we have a maze of twisty little passages, all different. We've got an entrance, we've got room A, and we've got room B. And when the maze is like this, mapping it out is really easy. We basically just we start at the entrance, we go left, we see we're in room A, we explore all the exits of room A, we explore all the exits of the entrance, we explore all the exits of room B. Because we can tell where all the rooms are, all we need to do in order to draw a map is navigate for a room, see where each of its exits leave to. If you are if the maze is like this, where you are in a maze of twisty little passages all alike, as in the classic game Colossal Cave Adventure, which the title is a reference to, here we're lost. There's nothing we can do, because all of these, no matter how we wonder about the maze, everything's always going to look the same. In the original game, the solution to this, spoiler alert, is that you drop items from your inventory in order to make the rooms distinguishable. But we're robots, and robots don't get pockets, so we can't take that approach. So we're not going to worry about this situation. Instead, what we're interested in is the question where we're in twisted little passages, which are kind of similar. I'm sorry, this doesn't render that well. So if you can't see the text very clearly, the top one says entrance, the bottom one says treasure, and everything else is a passage. So we have lots of rooms, most of them that look exactly the same. So we'll go and it'll just tell us we're in a passage, great, we're in another passage. And our job in mapping the maze is basically trying to untangle this mess and try and figure out which passage is which. For now, we're going to look at a smaller one, which should render better. So we'll start with just some simple models where there is an entrance, which is distinguishable as it's a room in its own right, and the rest are just passages. So here we've got the entrance. We can go left from the entrance, and we'll get to a passage. We can go right from the entrance, we'll get to a passage. But those two are not the same passage, and what we'd like to do in mapping out the maze is notice that those two are not the same passage and update our map to reflect that. So let's see how we can do this. We'll just sort of walk through the maze and see what happens. We are at the entrance. You go left, you're in a passage, as I said. You go left, you're back at the entrance. Now you go right, and you're in a passage. You're in a different passage, but we don't know that yet. But now we go left, and we're in a passage again. And something interesting happened there. The first time we went left, we got back from a passage, we got to the entrance. The second time we went left from a passage, we got to another passage. So even though these two rooms looked the same, we now know that they must be different rooms, because going left out of them doesn't do the same thing. If they were the same room, every route we could take out of them would have exactly the same result in terms of what we saw. So if that's not the case, they must be different rooms. And this kind of gives us the big idea of L-star, which is that we can use paths as experiments in order to distinguish the rooms that we're navigating around. a path here. And so our experiments that we're using here are that we've got the empty path, which is just you don't do anything and you look where you are. And we've got the path L, which is you go left once and then you look where you are. And this produces these tables of rows which allow us to distinguish the rooms. We've got the entrance is labeled EP, meaning if you stay there, you're in the entrance. If you go left, you're in a passage. The passage on the left is labeled PE, meaning if you stay there, you're in a passage. If you go left, you're at the entrance. And the passage at the bottom is labeled PP, meaning staying there is a passage, going left is a passage. And because each of these three rows is distinct, we know that they must correspond to different rooms. And so we've now learned something new, which is that even though we can only see two types of rooms, our maze must have at least three distinct rooms. And we've got a set of tests that let us tell which room we're in. For our mapping purposes, it will also be useful to label the rooms. And there's an easy way to label them, which is that we just give a room a name, which is some path that reaches it from the origin, from the entrance. So we've named the leftmost passage L, because going left from the entrance gets you there, and the bottommost passage R, because going right from the entrance gets you there. These names are not necessarily unique. We could just have easily have called the bottom passage LR if we wanted to. That's a perfectly valid path that gets us there. It doesn't matter what names we choose, as long as they are some path that will get you to the room. And the reason to use these names rather than just having the rows identifying them is that we're going to add more experiments later, and this lets us keep a stable name that doesn't change when we add more experiments. So here's an example of why we might need more experiments. If you look at this maze where we've got the entrance and then we've got three different passages which all chain together, and with our previous two experiments, the bottom two rooms, 2R and 3R, are not distinguishable currently. Like going left from each of them takes you to a passage, even though they're distinct rooms. But if we add a longer experiment, which is that we go left twice, now we can distinguish them. Because the passage 2R, if you go left twice, you get to the origin, to the entrance. If you go left, but if you go left twice from the passage 3R, you get to a passage. And so by adding this longer path, we've taken two rooms that were previously not distinguishable, even though they were different rooms. And we've now learned that, yes, these really are different rooms. We can observe a difference between them. That's not always going to be the case. Here is an example where, with each of these two passages, going left or right will take you back to the entrance. So any path starting from one must behave exactly the same as any path starting from the other, because the room you immediately end up in is the same, and so after the first step, they're always in the same room. So there's nothing we can do to actually learn from the description of the rooms what these passages are whether these passages are the same or not. We're not going to worry about that. For mapping purposes, we basically adopt the principle that if two rooms behave identically, then they may as well be the same room. This is essentially the same problem. The twisty little passages all alike problem. It's just like you have sort of like a sub-problem of the broader maze that looks like that. Yeah. So going back to our to this example, we have part of a map, which is that we know we have these four rooms. And we know that going right from the entrance will take you to room 1R. We know that right going from 1R will take you to 2R, just because that's the definition. And right, if 3R is the room you get by going right 3 times, 2R is the room you get by going right twice. So going right twice and going right once is the same as going right 3 times, because numbers. But what we don't know is what happens when we go right from 3R, and what happens if we go left from many of them. And the idea is that basically what we do is we add these sort of virtual rooms where, where you could name a room L, you could name a room RL, you could name a room 2RL, but we don't yet know that these are distinct, and they probably won't be. So what we do is we follow the path that takes to the room, and then we take an exit, and then we run the experiments again. And this tells us a bit about what the room we're in might be. And we can look at these sort of the right-hand parts of these, and these correspond to rows in our first table. And they can never correspond to more than one row because we've chosen our experiments so that the rows are all distinct. They might correspond to 0 rows. Like, it might be that we discover a new room in doing this, and if so, that's fine. We just add it to our list of rooms and start again. But it will never mislead us by giving us an ambiguous choice of room that this destination might go to. And so, sorry, 4-3 layout problems. And so by filling in this table and by looking up the rows in the first table that correspond to the destination, this gives us our map. And this gives us a complete map based on our experiments where we've managed to line them all up together. So this is how we can use these experiments to build a map of the maze. But where do these experiments come from? Like, I've just given them to you sort of out of hand right now, but like that was somewhat arbitrary choices. Would other experiments have worked? Like, where did I get these from? And the answer is that we find experiments by learning from mistakes. At any given point, either our map is correct, in which case we'll never make a mistake, or our map is incorrect, in which case at some point, like, things will go wrong. Like, we'll get a result where the map said one thing should happen and reality said a different thing should happen. And when that happens, that's an opportunity for us to improve our maps. Let's take a look at like how that works in practice. The left-hand one is our prototype maze but when we only have the experiments look where you are and go left. The right-hand one is the truth. So we go right, we're in a passage. We go right, we're in a passage. Passage. Okay, now we go left, we're still in a passage. And now we go left once more, and oh no, because we're still in a passage, but that's not what our map says. Our map has lied to us and told us that we should be back at the entrance now. So we know that something has gone wrong. And what we want to try and do is find an experiment that will allow us to fix that error. And the thing that's actually gone wrong is back here. Although we didn't observe the problem until we thought we were supposed to be back at the entrance, when we arrived in this room, this was not the room we were supposed to be in, because this is a room equivalent to the second passage, but we wanted to be in the third passage. And so everything after this misstep is an error. And you can see that because if you look at the two slightly grayed out, which doesn't show well on the projector at all, but the two bottom ones, left and left, those now are an experiment which distinguishes this room from the desired one, because going left twice from this room does indeed get you to the entrance, but going left twice from the real room we're in doesn't get you to the entrance. And so this is where our new experiment comes in. And you can see this by basically tracking what the rest of the path we're going to be taking is and what a name of the current room is. And so what we'll do is we'll sort of eat up one step at a time and look at the representations of the rooms. And see what happens if you navigate to being definitely in that room. So like you go back to the entrance, you go right once, say here, now you're definitely in room R. And now try what the thing you claimed was like the rest of the path from room R. There it is. And you keep going through this. And here is where the error happens and the result changes. Because going from 2R and then doing RLL takes you to a passage. Going from 2R and going LL takes you to the entrance. So that change point is what we're interested in, because that's the thing where the misstep happens. And it stays as E afterwards, though it could change back. And when we do this procedure of like replacing the bit where we think we currently are, sorry, the bit where we currently are with the bit where we think we currently are, there will always be this change point, because when you started out, what this is showing is the true end result of following that path. And when you stop, you what you get is the predicted place label of this path. And because we made a mistake, those two must be the same thing. So this change point will always happen. And the first point at which you change is going to be our new experiment, because that is the bit where we can tell that, the first bit where we can tell that we've made an error and that there is a misstep. So let's see how this works with a larger example, which is our initial complicated one, where we're trying to find treasure. We start out with a single experiment, which is just look where you are. And this gives us this very simple and completely wrong map on the left, where you go from an entrance to a passage and back again. And the thing that can demonstrate this as an error is if you go right twice, then in our map here, going right, right, and going right twice will get you back at the entrance, but going left then right will not. It will get you to another passage. So this has told us that these two immediate passages we can get to from the entrance are distinct. And so we update it to this model. And then we need a much longer path to find the error, which is if we go left 4 times and then go right, this gets us to treasure. We like treasure. And we can do this, but we can do the same construction to find the bit where we go wrong is the bit where our true path takes us to treasure, and the path we thought was equivalent to the true path just takes us to a passageway. And so we add in the experiment LLR and get this more complicated map where we've distinguished a few more of the passages. We still don't have a perfect map, but now we're at least sort of getting to places where we can figure things out. And it turns out even with this new experiment, we're still going wrong with the same result of going 4 L's and R. It's just that we go wrong slightly later. And in order to fix that, we add this change point again, the LR experiment, which distinguishes our wrong transition. And now we are correct. GraphViz does a different layout for some reason for these, but believe me, these are the same maps. Because now we've got a rich enough diversity of experiments that we can distinguish all the different rooms, and we've figured out that all of these passages are really actually distinct. And we now have a treasure map that actually works to find treasure. So just to recap, the core of the algorithm that we discussed, you start out by using descriptions to distinguish rooms. Like the entrance is not a passageway. A passageway is not the treasure room. If you can see a difference, you don't need any help to distinguish them. And then you extend this by using paths out of these rooms into other rooms we know how to distinguish, to be able to say, okay, well, even if these rooms look the same, going left from them produces different results, so they're different. And we can use these experiments to build a map, because the experiments let us orient as to where we are, and once we know where we are in the maze, we can find out how everything ties together. And as long as our map is wrong, we can always learn a new experiment that will improve it. And we can do that by looking at our mistakes and fixing our mistakes. So why is this interesting? The first reason it's interesting is just this ties into a huge area of research called formal language theory, which I really like and is the basis of a lot of important technologies. And Samathy will be talking later today, I think, about how it gets used in regular expressions. And also, it's just really pleasant and elegant, and I enjoy it. But the thing more about this is it lets you turn black boxes where you just have something that does something and you have no idea what it does into precise, easily describable models of the system. So there's a lot of good papers. I don't know if there are good tools yet using this in testing, where you take a Android application, say, and you can basically just click around on it randomly, and exploring the app is like exploring a maze, and you build these automata models which model how the app behaves, and can then start proving things about the automata. And as long as the map is correct, things you prove about the automata, you can also prove about the application itself. If you want to read more about this, the original paper is Dana Angluen's Learning Regular Sets from Queries and Counterexamples. The presentation I've given of it today uses some results from a later paper by Rivest and Shapire. And I've also written a blog post about this, which is much more formal and mathematical than the talk I've given you today, and sort of goes into a bunch of the fine-grained, hairy details. These slides are all available, by the way, and so you can look at these references later, and some of these are working links. And so, yeah, that is all I have to say about L-star. I hope this has been a somewhat interesting look at a weird algorithm that almost nobody knows about. Thank you very much.
Cool, thank you very much. We have 5 minutes for questions. Samafi.
So I can see this being useful in the cases where passageways have passages into themselves, so where nodes have a transition into themselves. If you removed that, is L-star search still useful, or does it become less useful than, say, just following all the right passages 5 times, and you know that if you follow a right passage 5 times and such?
So having passages have loops into themselves isn't really that necessary for L-star. It's this should work with pretty much any automaton model. The question of whether L-star is useful ever is somewhat harder to answer, because part of the problem is that it's fairly expensive. But I must admit, I'm not 100% sure I understand the question, but no. But basically, like the thing that L-star lets you do is it lets you tell whether 2 passageways or rooms are genuinely are distinct or not. And so it's a good way of building up a transition model of where everything fits together. If you just want to find your way to the treasure, you don't need L-star. If you want to build like an actual treasure map or a map of the maze that gives you more information about where everything is and lets you model the automaton a bit better, that's where this is useful. Like the main assumption, which I glossed over, is that you always need to be able to find your way back to the entrance there.
Cool, we've got time for another couple more questions.
So I actually have 2 questions. The first is, what's the computational complexity? And the second is, what happens if you have more than 2 directions on each node?
Let's take those one at a time, I think.
Okay, so the computational complexity is slightly, it depends. But essentially it ends up being, in order to complete the table, you need to, and find all the exits, you need a number of queries, which is the number of rooms times that you know about, times the number of experiments, times the size of the alphabet. And this is part of why I've very rarely used it, which is that if your membership queries are remotely expensive, then it does end up being kind of prohibitive. There's also a question of like, the complexity really depends on how long it takes to terminate, which depends on how small the actual maze is. So if every time you make a mistake, then you learn a new room, and you have to rerun the completion process. And if there aren't that many rooms, you won't make very many mistakes. If there are billions of rooms, then like the complexity is dominated by the fact that you're running the core loop billions of times. The answer to what happens if there are more than 2 exits is it works exactly the same. It works on any alphabet size, but the completion step, you do have to try every character or every exit to every room, and so like it acts as a multiplicative factor.
Cool. Any further questions? No? In that case, thank you very much, David.
Thank you, John.